There's plenty of people making camshafts for turbocharged diesels, but nobody making camshafts for supercharged diesels. Until now. And I'm going to show you how it works.
Banks built, protected by AMSOIL, with support from Roadster Shop and Nitto.
For about a year, we've been working behind the scenes to come up with a cam for lockjaw. It seems that nobody makes a cam specific to supercharged diesel engines. So we decided to make one. When we're done, you'll be able to buy this cam in a Banks box, and it'll say right on this side of it, Banks blower cam. Before we get into measuring the cam on the Cam Pro Plus, I want to get into what's different in the valve gear area on the L5P. So let's just start with the cam blank in the test fixture. This is a cam core or cam billet for an earlier Duramax engine prior to the L5P. And it's got an oil groove in the fourth cam journal that isn't there on the later camshafts. And the lobes on this cam blank are wider than an L5P. That groove in the fourth journal was for lubricating the turbocharger. That's all been changed on the L5P, and it gives you much better oiling elsewhere inside of the L5P by eliminating that system. So if we go over and we look, here's a stock L5P cam with the earlier one next to it, and you'll notice that the lobe width is different, L5P being narrower, and you'll notice on the fourth cam journal that groove is gone. And when we go to production on these blower cams and also the turbo cams for the L5P, we will be using a core specific to this design. Now, why are these things narrower? Let's talk about the tappets. And we'll start with the LML roller. This is LML or earlier. These things weigh 202 grams. The roller diameter is 944 thousandths across the width of the roller, and the body diameter is 1,790. This is a stone. This thing is incredibly heavy. It's a bushed roller, so there's no needle bearings in it. Then we go to the L5P roller tappet. Much smaller, 137 grams, roller diameter 700 thousandths, and you can see the needle bearings inside there. And the body diameter is 921 thousandths. This roller diameter of 700 thousandths is the same as on the Chevy LS engines. So they've pulled some LS technology into the diesel engine, which is incredible when you think about it. They've got a roller system that's worked in probably millions of engines at much higher engine speed, and they brought that tested piece in a new body diameter directly into the diesel. The body diameter of the LS is, I believe, 842 thousandths, like all the way back to 1955 Chevy small blocks. And it has a couple of flats. The roller has to be guided so that it's always aligned with the cam lobe. You don't want them turning sideways and skidding. There's a cassette, a guide cassette, which is kind of a composite material that guides four rollers, very LS in a diesel. And the third roller I wanted to show you is a Jessel. This is 95 grams, and this is basically a pro stock type or pro mod type, very high RPM tappet setup, very light, 850 thousandths roller diameter and a 935 body, which tells me if I want to go to these in my L5P, I machine 14 thousandths out of the lifter bore and put in a key groove to guide it. There is a key right there on the upper part. And I'm good to go with lightweight lifters in my L5P. Now, moving to the cylinder head itself, you've got 4 valves per cylinder. You have 1 rocker for the intakes, 1 rocker for the exhaust, and they have 2 different rocker ratios, which makes for way different lobes on the camshaft in terms of the height of the lobes. Unique to most diesel engines with 4 valves and 1 rocker per pair of valves is a valve bridge. The valve bridge bridges the 2 valves The rocker presses in the center of the bridge and opens both valves at once. What's mission critical here is the valve springs. Both the valve springs need to have the same seat pressure, the same spring rate, and consequently the same open pressure. Otherwise, as you start to open the valves, one will lead the other. The one with a weaker spring will lead the one with a heavier spring. Why is that important? Well, I don't want the valves to hit the pistons, and we are getting real cozy with that. So we can't have wildly different valve openings. That'll become really apparent in a few minutes when we look at the valve to piston clearance on my cam plots. What we've got here is a Cam Pro Plus from Audi Technologies in Norristown, Pennsylvania. This is damn near rocket science. It's auditechnology.com. And if you're at all into camshafts and their measurements, flow measurements, he's got flow bench stuff, he's got engine simulation software. So what do we measure here? I'm going to ask Mike to come in and start measuring this camshaft. Come on in, Mike. And we'll see on the screen, as it acquires data, there's a spherical follower here, and this is the encoder, and this encoder that follows the lobe, so to speak, is microscopically accurate in its resolution. I mean, it's like to the micron. It's insane. So you don't want to be stomping your feet around this thing because you can see it in the data, just you walking into the area. So Mike, if you can start, this is a motor-driven device. It has a rotary encoder here, and it has a linear encoder here, taking this cam rotation and turning it into lift versus angle. That's what all pours into the computer system. So let's start it running, and I'll tell the guys here what we're measuring. You'll see at degrees and lift, we're zeroed out, and here goes the process. First thing you do is you enter the lash and the rocker ratio into the device, and that's used to compute valve motion. The thing measures base circle runout, lobe lift, clearance ramps, valve lift, duration at our assigned lift points. The base circle is measured to within 5/10,000ths of an inch. It also computes the area under the curve, which we'll get into over here on screen, the lobe centerline locations, the lobe separation angle, the valve overlap, and this is really important, the cylinder to cylinder phasing of the lobes. If you've got an engine that's firing every 90 degrees, you want the valve action to be every 90 degrees. And in the old days, a lot of cams were ground with individual cylinder masters. So you set these masters up on the cam grinder, and you had a follower that followed each master. If they were shifted and not in proper relationship to each other, then you had different cylinders with different valve action. What that gives you is different power out of each cylinder, and that leads to power imbalance. In other words, you dynamically balance the engine, and in the case of this V8, you want 8 cylinders making exactly the same horsepower. You've got it balanced in terms of the dynamic mass issues, but if the power is different, the engine vibrates or shakes as a result of that, and the crankshaft has induced torsionals that if it's big enough amplitude, you can kill the crankshaft. Not instantly, but over time. So that cylinder to cylinder relationship we also get. We're able to measure the tappet and valve acceleration, the tappet and valve velocities that you reach. Basically, to set the encoder, we set a TDC preliminary position between the lobe centers, in the midpoint between the lobe centers. and then we dial in the specified advance. This has already been done here. We have now got the cam relationship to the crankshaft exactly dialed in. The other thing that's kind of cool about Audi's equipment is you can take these encoders and you can measure the camshaft in the engine, Tappet as well as valve. I like to know what's going on when it's in the engine in the final analysis. So this is data from the cam itself and then the cam in the engine. Now you're including all the valve gear, which sometimes deflects as you load up, opening the valves, etc. You can actually do it here, calculate using the rocker ratio, subtract the lash, and come up with what the valve lift should be. You go into the engine, you've got the valve spring pressure now acting against the system, so you get valve gear deflection. And sometimes that removes 10 or 15 thousandths of valve lift. And when we're measuring it cold, the deflection can actually be greater in a running engine than it is in our cold measurement. Let's take a look at the screen and our results. We've got two traces. The lower one is the cam itself, and the higher one is the valve action. Why is the valve action lifting more? Because it's multiplied by the rocker ratio. So it's cam times rocker ratio equals valve. So now let's take this and put it in the engine. We'll do that on the other screen. So we've done two experimental grinds, what we call the Banks 400 and the Banks 500. That has to do with gross valve lift. This is the stock cam that we've got up here, the L5P grind. The exhaust lift is 371 thousandths and the intake is 385 thousandths. Here's the 4 strokes: power, exhaust, intake, and compression. Pistons at top dead center. The cylinder pressure is rising because combustion is underway, and somewhere around 8 to say 16 degrees after top dead center, you reach peak pressure. Now, peak pressure depends on engine load and a variety of other factors, so it's not consistent. When I talk about peak pressure, I'm usually talking about wide open throttle at that RPM. So we reach peak cylinder pressure somewhere in here, just a little after top dead center. The piston puts power into the crankshaft through the connecting rod. This is the only stroke where power is produced in the crankshaft. All the other strokes, the exhaust stroke, the intake stroke, and the compression stroke, use power for the exhaust to pump the exhaust out, for the intake to draw the intake in, and on the compression stroke, you're building heat and compressing the air in the cylinder. You get a little of that back on the power stroke because it's like an air spring. You're compressing the air and heating it, and then when it fires, it expands. So there's a little payback there, but there's still power used out of the crankshaft on the compression stroke. So let's take it from the blowdown intercept. Valve starts opening, and at bottom dead center, you have a finite valve opening amount. And this little triangular shape represents the flow of exhaust before bottom dead center. That's the amount you blew down out into the exhaust system prior to the piston reversing direction. This is an important point, and we'll talk about it more as we go. The area under the curve represents, to me, it represents mass airflow or mass exhaust flow. We need more area if we want to flow a greater amount. With a supercharger, we don't have a lot of back pressure retarding the flow of the exhaust into the exhaust manifold and out to atmosphere because there's no turbine section of the turbocharger present. With a turbocharger, the back pressure, the pressure resisting flow from this point all the way through is pretty high. On street-driven setups, especially under acceleration, it'll exceed the boost significantly. Let's say you're 40 pounds of boost, you might be at 50 pounds of exhaust pressure. So you're exhausting against 50 pounds of pressure. With a supercharger, you're exhausting against virtually no pressure. So it's vastly different. And that reduces the exhaust pumping losses. It reduces the power used to push the exhaust out of the engine. It also reduces the exhaust gas temperature, the heat that's rejected into the valves, into the piston is reduced. It's just easier on the engine as regards heat rejection, and that also includes the piston. You don't need as much piston cooling at a given horsepower with a pure supercharged diesel engine as you do with a turbocharged diesel engine. So everything gets happier in that respect. So the point where we open the valve, I'm calling the blowdown intercept. So the valve begins opening. The next point I want to define is the lift at bottom dead center. This has to do with how much we're getting on the exhaust port, how much we're getting on the flow out of the cylinder. The amount of flow, if you just look at this little red dashed line and the trace for the valve lift, this area designates, it's kind of dimensionless, but visually demonstrates the flow before bottom dead center. And that's a comparative I'll show you on the other cams. Area under the curve has to do with a comparative I'll also show you on the other cams. We reach peak lift on the exhaust, in this case 371 thousandths, and we begin closing the valve as the piston is now reaching top dead center. As you're reaching top dead center, the valves start getting close to the piston. So this represents the valve lift, and this dotted line is the piston clearance to the valve. So you can measure vertically at any point all the way up here between the two, and you know the clearance between the valve and the top of the piston. We're not putting valve reliefs in these pistons. I'm running a program where I don't want to screw up the swirl of the gases in the cylinder and mess up the combustion process with valve reliefs. So I'm going to see how far can you go with no valve reliefs whatsoever. Quite a bit of clearance is available here, and we close the exhaust valve after we open the intake valve. That's called valve overlap, and this is valve overlap at zero lift. In other words, this lower line is zero valve lift. So we've kind of defined zero lift overlap, and there isn't much going on here. This is how the factory does it, though. You don't get a lot of opportunity for the incoming intake air to push out the residual exhaust. But understand, for a stock engine that also uses exhaust gas recirculation, so a little residual exhaust probably doesn't hurt them much. But it does hurt you in this respect. There's residual exhaust, and that's replacing oxygen in the cylinder, so to speak. Intake starts opening, and the overlap is actually after top dead center, what little there is. Here we get the intake to maximum lift, which is 385 thousandths. Piston is dropping down the bore, inducting air, and as we get to bottom dead center, the valve is still open. Why is that? Because we've got enough momentum in the air to continue putting air into the cylinder until the point that we close the valve. Now, if we stay open too long here, we start shoving intake air backwards into the port. You don't want to do that. So you don't want to close too late. But as you go up in RPM, you do want to close later and later. It's all a function of how much time you have. As RPM goes up, the time for all this flow to occur diminishes. So you want to move the cam around a little to account for that. We have to also close the intake in time for the air to be compressed and heat up enough so that when you inject the fuel, and virtually instantaneously you have ignition in a modern diesel. There's virtually no ignition delay anymore to heat the fuel, and then it starts to combust. The combustion is virtually at the same point in time. The minute you inject, you're starting to build pressure in the cylinder. You're on the compression stroke, so you're already building pressure, you're already building temperature. Now you inject, and the cylinder pressure really starts to rise. So from the point of injection to top dead center, you're doing negative work. Your combustion is trying to push your piston backward down the bore. The goal is to inject as late as possible. Now, this is the main injection. There's also some pilot injections that take place to get the process going and minimize the combustion noise. There's a number of benefits to pilot injection. And there's some injection that takes place after the main that has to do somewhat with emissions. There's the whole process. The clearance to the intake valve is the solid line here. It's a little bit different relationship. So I think I've covered everything on the graph. Let's go to our 400 grind. Now you're going to see some differences real quick here. We're holding to 400. This is a grind that allows us to use the factory valve springs. The 500 requires a different valve spring. You notice the blowdown intercept is now earlier, but with the blown engine, we're not at 2,800 RPM for peak power. The minimum we're going to turn in the engine now is 3,800 RPM. So we have less time for that blowdown to occur. We're opening the valve sooner, so the blowdown intercept has moved significantly. The lift at bottom dead center is also greater, which increases the flow rate as the piston starts up the bore. The exhaust flow is really starting to truck. And look at the change in flow before bottom dead center. It's now this plus this. The lobe area, we've increased 26%. That doesn't mean it's going to flow 26% more. That's a relationship I'll be talking to you about as we measure mass flow with the new cams. By that I mean mass airflow into the engine and consequently exhaust flow out of the engine. At the overlap area, you'll notice that the overlap zone is now greater. The overlap position is now advanced. The overlap triangle is now visible. It's still not a lot of overlap, but with a blower, you don't want a lot of overlap. That's the point here. To understand that, let's look at the intake. Here comes the intake, drops down. We're closing the intake at the same point. We're not changing this much. I want to make sure that the engine starts. Why does this affect engine start, especially in cold weather? If you start closing the intake later on the compression stroke, in cold weather you're inducting very cold air, and if you close too late, you don't have enough time to build the BTUs, the heat energy, to a temperature level that allows you to fire the engine. Now there are cures for this. They're not pretty, ether being one of them, injecting ether. But this is going to be a street setup. It's going to run anywhere in the United States as far as I'm concerned, so I'm being conservative here. I need to add, we picked up the 27% area increase on the intake lobe. We're keeping the overlap minimal because I don't want to supercharge the exhaust. When both valves are open and you have very little back pressure and we're expecting somewhere around 30 pounds of boost, maybe a little over with the blower, not as much as with a turbo, but there's positives and there's negatives. This exhaust back pressure thing is a huge positive. We don't want both valves open at the same time for too long. Otherwise, we'll be taking boost air and blowing it through at overlap into the exhaust manifold. We don't want to supercharge your neighborhood. We want to supercharge the engine. That's what that's all about. All right, now we're looking at the 500. Lift is 500, both intake and exhaust. 52% area increase on the exhaust and a 54% area increase on the intake. Notice we've doubled the increase at 500 thousandths lift. Blowdown intercept a bit earlier, much more lift at bottom dead center, almost as much lift as a stock cam. And a great deal of exhaust mass out of the cylinder already. As far as valve piston clearance is concerned, both the 400 and the 500 get relatively cozy compared to stock, this being stock here. We're getting much closer to the piston. Our overlap triangle is virtually the same as with the 400. We just don't want those valves to get too cozy with the piston. And remember, I talked about balancing the valve springs. This is with everything balanced. We've got to have some clearance as the valve springs, even if they're matched, they won't degrade equally. I want to make sure that through the life of the engine, the valves never smack the pistons, or the pistons never close the valves. So what does this mean? Well, power is all about airflow, and this is all about increasing the airflow. So at 2,800 RPM, where the stock power peak is, this is going to increase airflow significantly. But what we're looking to do is move the power peak up 3,800, 4,000, 4,200, somewhere in there. So we intend to turn this Whipple 3.8 at least 4 times crank speed, starting at 3,800 if possible. I kind of view this engine program as something we would want to do as a production engine. In other words, offer a supercharged crate engine. And my power goals are pretty well up there. I'm hoping for eventually an even larger supercharger from Whipple. I understand they are working on one, what they call a Gen 6. So the whole idea is, I've only got so much boost available. If I open the valves further, if I keep them up and open longer, I'll increase the lobe area, I'll increase the area under the curve as far as valve action is concerned, and at each RPM you select, we're going to have one heck of a lot more airflow at the blower boost output. So although you can turn the stock L5P faster with a stock camshaft, the horsepower just falls off the edge of the world. There's no airflow, it's choking it off. What we're looking at here is opening the valves higher, that'll give you additional flow, and cycling the valves, firing the cylinders more times per minute. So that'll give you more power impulses. The two combined, moving the power peak up, so you more air, more times per minute, that's the formula, the ingredient we need to make our power goals.
In the next episode, ATS builds our transmission.